Okay, I decided to tape a little more for you guys, and so the subject that I am going to approach in this lecture is an introduction to the question of damage localization. We are here, the course, you know, it's vibration-based structural health monitoring, identification, and so on. So thus far, we've developed some understanding of how from data we can go, excuse me, let me turn this thing off. Yep. How from data we can obtain an identification of the system. Whether we have input-output data, we can get a realization A, B, C, D. Or if we only have output data, we can get a realization AC, let's say, in the elementary methods that I presented in the last lecture. From these realizations, we can calculate modal parameters, natural frequencies, damping, mode shapes, and this can be viewed as being a compressed version of the system characteristics. And so if damage takes place, one can then attempt to make that distinction, make that assertion by inspecting how, for example, the frequencies changed, right? Or in some cases by how some mode shape may have changed and so on. And there are, of course, many problems and many methods and so on. So the point right now is not going to damage detection, that is, making a distinction between whether this identification result is the same as that other identification result, but actually let me take one step ahead and assume that we are satisfied that our structure has been damaged. We will certainly address the how to decide later, but let me just say that we are satisfied that our structure has been damaged, and what we wish to do is to gain some information as to what is the location of this damage, okay? Where? There are a collection of methods, they are all from the same family, that we've developed here starting in about 2002, which are called the damage locating vector procedures. There is a sequence of papers that begins in 2002 and goes up to about 2010 or something like that, that contains the various techniques. Well, the various members of the family, if you'd like. So what I'm going to do today is just introduce the basic one, which is the DLV scheme. So our objective is to learn something about damage location, right? And in this particular discussion, we are going to do it with the DLV approach, and that stands for damage locating vectors, okay? Damage locating vectors. We are going to assume in our discussion now that this is a case of known input and known output. So we have input output data. And from the input output data, we have done what we already know how to do, and we've obtained a realization A discrete, B discrete, C discrete, D discrete, and from that realization we've done a D2C, and we have the continuous time, right? And so we have AC, BC, CC, and DC perhaps, okay? Input-output data, and we could say that this occurred on the reference state. Because what we call damage is really just a change from some state to another. The structure, in principle, could be damaged right here. doesn't matter. This is what we're calling the reference. And what we seek to find is at another time, which we would call the interrogation time, right? At the time of interrogation, we also have input-output data, and we've done exactly the same thing, right? We have our A, B, C, and D. We've done the D to C, and we've obtained the parameters A, B, C, and D. And of course, as I said, we are satisfied that these two things are not really the same. They will never be exactly the same, right? Because there is noise, there is this, there is that. But the change that we've perceived on the eigenvalues of A, for example, are large enough that we've decided, okay, this structure has suffered some damage. We would like to have some information on the location of that damage. Okay, so up to this point, we have no model, right? Because we can do this simply from input-output data. We are here. This is all purely data analysis. Now, let's zero in or focus by having a specific structure here just to focus ideas. So let's say that our structure was like this, okay? And that our structure had one input here and outputs here, 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 and here. So in red we have outputs, and in the brown that I am using throughout, excuse me, we have inputs. Okay? Now that means our system, because of degrees of freedom 1, 2, 3, 4, 5, right? So in this case, assuming the data was very high quality and so on, we would identify a system of order 10, right? Because 5 degrees of freedom would be order 10. Our C matrix would belong to real in continuous time after passing it, right? And it would have how many rows? 1, 2, 3, 4, right? So it would have 4 rows and 10 columns. That's what our C matrix would be. Our B matrix would have only 1 column, and it would have 10 rows, right? So this would be a 10 row by 1 column because we only had 1 input. Our A matrix would be what? Real again, because that's how we normally output it, and it would be 10 by 10. And would there be a D matrix? Well, that depends on whether these guys are accelerations or whether they are displacements. Let's say, to throw a little twist, that they happen to be accelerations. Okay? So if they were accelerations, then we would have a D matrix because there would be a collocation here, right? And the D matrix would be R, real. It would have 1, 2, 3, 4 rows, and it would have 1 column, right? Because it has 1 input and 4 outputs. And so those would be the matrices we have. Now, here we have to decide now, this, let's say this is in the reference state. We are in the reference state. We already did the ID, got it in discrete time, passed it to continuous time error here. Now, the first thing that we could do at this point is say, well, I want to expand my system to the union of the experimental coordinates, right? Because I have a collocated input-output here. Therefore, even though my transfer matrix G is C identity times S minus A to the minus 1B plus D, in this case, right, for acceleration. Even though that matrix is only one column, we know how to expand by taking advantage of the symmetry of the matrices MCK. And that is in the prior lectures, last two lectures, and there was even an example and so on, right? So let's say that we go ahead and apply our procedure to expand the matrix, this here. So when we finish, in this particular case, there are no inputs by themselves, right? So all that will happen is that when we finish the expansion, the matrix C here will have, I'm sorry, not the matrix C, the matrix B here will have not one column, but will have 4 columns, right? Because what we're going to do is to say that GS, right, is equal to the summation, oops, the matrix GS is going to be the summation of the residues divided by S minus lambda J, right? And the D is a little bit awkward right now to handle because I'm not really going to expand the D, although I could, but let's just say that this will not be needed. Okay? Because this was for acceleration, and eventually I want to go back to displacement, okay? So this is for acceleration. Now, actually, you know what? I think now that I'm doing it, that it might be a little bit more consistent mathematically if I do it in the following order. Okay? So, forgive the change. Let's say we are here. It's a little bit more consistent. Instead of having to write not necessary now, let's just do it this way. So I have the acceleration transfer matrix here. What we want to do first is get the displacement one. So for the displacement transfer matrix, if I have my matrices C, A, B, D, all I have to do is to replace the C, which was C displacement, right? Which was C acceleration. I have to just replacement by C displacement. But if I remember correctly, we said that C displacement is equal to C acceleration multiplied times AC to the minus 2, right? Therefore, we can take, is that true? No, I think that's backwards. Wait, I think we have, wait, I should have checked the notes. I'm just doing it in my head quickly, so we get AC squared. So C displacement by AC squared is C acceleration, right? C acceleration is C displacement by AC squared. So that's it, right? Okay, I can write it to the minus 2 if I want, but it is C acceleration is C displacement by AC squared. So that means that if I have C acceleration here, I can just simply write C displacements C displacement is equal to C acceleration times a to the minus 2, okay? So I just simply replace the formula for displacement needs to have C displacement here, okay? And what we have is C acceleration, so we put our C acceleration times a continuous to the minus 2, and now we have, with no d, the expression for the displacement transfer matrix. Okay, sorry for that, I'm just kind of doing this on the fly, and I don't have notes looking at it, but basically this is it. C acceleration is C displacement AC squared, therefore C displacement is CA, a to the minus 2. This is the expression for the transfer matrix when we measure accelerations. What we would like is the transfer matrix for displacements, and what that means is simply that here we should have the C for displacements, and we don't have a D. And the C for displacements is the C for accelerations, which we have, times a to the minus 2. We put that here, and we have our transfer matrix, right? Now that transfer matrix is still just one column, right? Because this B is still just one column. So now at this point, we expand. And when we expand, this one, let's say, is complex depending on the C, but it is m rows by one column, right? So now that when we expand it and we recognize the distribution of the sensors, we now will have a transfer matrix displacements, function of S, which will be just this expression here, right? But it will be complex, and it will be 4 by 4, right? So the transfer matrix for displacement 4 by 4 we can calculate from here. So to say it all briefly and fast, without making errors, hopefully, we have a situation with 4 outputs and 1 input. They are accelerations. We do the identification. We get this, A, B, C, D. In discrete, we pass to continuous. Once we have it in continuous, we would have, if we wanted to evaluate the transfer matrix at an S, we would plug it in here. We would get one column. Why one column? Because only one input. However, we would then, and also relating accelerations to forces, we then introduce the relationship that we have over here and get the transfer matrix for displacements, still one column, and then that's by the AC to the minus 2, and then we just simply say, okay, apply the theory that we learned about expanding. We're expanding, now we have the transfer matrix at all coordinates, what I would refer, all coordinates that have measurements, which is self-referencing, so we have a 4 by 4, okay? Now, this procedure that we have right there would be done on the reference state, and then it would be done on the damage state, all right? So what we have is simply that in the reference state, we have A, B, C. We don't need any D's, right? Because we already passed to displacement. And in the damage state, let's call those 1. And in the damage state, we have the same thing. AC, BC, CC, and let's call these 2's, right? And that's what we have. Now, the transfer matrix, G, relates forces to displacements. So you can say that the displacements as a function of S are equal to the matrix GS times the forces US, right? That's what the transfer matrix says. It's an algebraic connection between forces and displacements. In our case, this transfer matrix is 4 by 4, and it gives us 4 outputs, and it is handling situations if we had 4 inputs. Even though in the test we only had 1 input, we just learned all this other stuff for free due to symmetry, right? Okay. Now, the transfer matrix, if we go back to fundamental structural analysis, we know that in analysis, statics. In statics, we say that the stiffness matrix times the displacements of a model are the forces, right? So if we invert the stiffness matrix, we say that the displacements are equal to the inverse of the stiffness matrix times the forces, right? The inverse of the stiffness matrix is what we call the flexibility matrix times the forces, right? So the matrix that connects the forces to the displacements in a static problem is the flexibility. Now, this is exactly the same thing, forces, displacements, except in the Laplace domain, right? But it turns out that if we evaluate Laplace results at s equal to 0, that is the same as operating in statics. So the transfer matrix evaluated at s equal to 0 is the flexibility. All right? So, with that in mind, that the transfer matrix evaluated at s equal to 0 is the flexibility, we can now see that the flexibility matrix, okay, in state 1 is just going to be CC1 times what? The identity times S minus A, but S is 0, so we just get AC1 to the minus 1 BC1, right? And that's the flexibility in 1, and I need a minus sign here because this was identity times S minus A. So that's the flexibility in the reference state, right? Now, that flexibility in the reference state is a matrix that is 4 by 4, and it is exactly the meaning that you have from structural analysis. F1